Thank you very much for the introduction. I'm going to present a collaborative work today between the Laboratory of Mechanics, Modeling and Sustainable Processes, in which I am, and the Laboratory of Chemistry and Environment. Both of these labs are in Aix-Marseille University. So to begin, let's remember that microplastics are particles typically from 1 micrometer to 5 millimeter in size. And they can come from two different sources, primary sources, where these products that you can see on the screen can directly release microplastic in the environment, and secondary sources where big plastics degrade into microplastics. So we can find microplastic everywhere in the soils, in the air, and in the waters. And so we need to increase our knowledge of the levels of contamination of microplastics in the environment. But at the same time, the problem is that we can be in contact through direct or indirect ingestion, inhalation, and skin contact. And so there can be potential physiological effects due to the physical or chemical properties of the microplastics. And also it can have an impact on the human health. So we need to find processes to reduce the discharge of microplastic into the environment and or reduce the contact between humans and microplastics. So in this context, our two main objectives were the following. So the first one was to accurately analyze the number, the size, and the type of microplastic in very different waters. So we decided to focus on waters using FTIR spectroscopy, but we needed to adapt this analytical method to real complex water and assess the microplastic pollution in these samples. The second objective was to assess the efficiency of different processes to remove microplastic from real water treatment lines, and we did a focus on the ultrafiltration process, which is a common membrane process with a pore size of 20 nanometers, which theoretically could retain all microplastics. So here you can see a map of France with our sampling sites. So we had a seawater treatment line near Nantes for aquaculture applications. We had a drinking water treatment plant near Paris, and several other drinking water treatment plants and wastewater treatment plants in the southeast of France. So the treatment plants in gray, I will not show you the results of these treatment plants today. So the samples were collected in glass bottles, stored at 4 degrees, and then were brought to the lab where we could perform the FTIR methodology. So the sample were first filtrated through a 25 micrometer stainless steel filter, followed by a 5 micrometer gold-coated filter, and both filters go to the FTIR microscope provided by Perkin-Elmer, using a reflectance mode and a 6.25 micrometer pixel resolution. Then the FTIR image file goes to a freeware called the Simple, and this software can identify 23 materials, among which 15 plastic polymers. But for some samples, especially those with high turbidity or high total organic carbon concentration, we needed to pre-treat these samples, so we used oxidative digestion to remove organic matters, cellulose, or proteins. And if calcium carbonate was a problem on the filter, we used acidification. And of course, we made sure that there were no or very few effects of these processes on the microplastic characteristics. And some samples did not need pretreatment, such as all the sample at the end of the treatment lines, and ultrafiltration permeate also. So let's move on to the results. If we start with the case of the wastewater treatment plants, you can see the different colors represent the different types of microplastics, and you can also see the concentration of microplastic in log scale for two wastewater treatment plants. So you can see that in the influent of both wastewater treatment plants, we have a high amount of microplastics. But good news, these wastewater treatment plants already can remove more than 98% of microplastics, as you can see in the secondary effluent. For the second wastewater treatment plant, we added a tertiary treatment process for water reuse purposes, and we wanted to see if we could retain more microplastics. So the answer is yes, as you can see here. UF can increase the total removal rate of microplastics. If we look now into detail about the dimensions of microplastics, so first an explanation of how we get the sizes. So the software identifies the major dimension of each particles, and imagine the particle as an ellipse, consider the particle as an ellipse, and then draw a minor dimension. So you can see on these two graphs the minors and the major dimensions, and the concentration in each of these dimension ranges. So what we can see is that UF can decrease the microplastic quantity in each size group, in each square, but also it reduces the dimension ranges of the remaining microplastic particles as we are in this square of the minor dimensions. But still, we have microplastic with a size higher than the pore size of the membrane. And here, so we can assume a possible contamination of permeate by the pilot plant, the pipes, which are all made of plastics. Now, if we look at the case of the drinking water treatment plants, so you can, in log scale again, so you can see that after UF ultrafiltration as a final treatment, we could remove more than 80% of microplastic in quantity. But in the tap water, we still have some remaining microplastics, such as polyethylene mainly, and a bit of polypropylene also for the first drinking water treatment plant. And finally, for the case of the seawater treatment line, so used in shellfish farm for aquaculture applications, you can see the different processes of our treatment line. And after the zeolite filter, you can have UV or 2 UF pilot plants that I will explain to you in more detail. Here you have the different locations of where we took the different samples. And I want to draw your attention to the UF pilot plants. So we had the old UF pilot plant here because it was in operation for more than 4 years. And we had a new UF pilot plant that worked for less than 1 month here. But all the 3 samples, are after the zeolite filter, same sample. So if we look at the results, so in the seawater, you can see that we have more than 400 microplastic per liter. Here, the log scale was not needed. And if you look at these 3 samples, which theoretically are the same sample taken after the zeolite filter, you can see that there is an increase of microplastic concentration, which could be potentially because of releasing or degradation of microplastic through the zeolite filter, degradation or fragmentation from big particles to several smaller particles. We have almost the same amount, but if you look at the colors, we have also a different distribution of types, which could be because of the different time of sampling or different pipe materials between the 3 processes. And if we look at the ultrafiltration at the end of the line, you can see that the new UF membrane seems to remove better the microplastic than the old UF, probably also because of degradation of plastic pipes of the pilot plant of the or permeate pipes, yes. So in conclusion, we could assess the number, the size, the type of microplastic in very different water, freshwater, seawater, and wastewater. We could see that plastic contamination from processes or pipes could be suspected. We could assess the retention efficiency of different treatment processes with a focus on ultrafiltration, which showed a great retention rate for all the different treatment lines, but we still not reach 100% as expected. So here the assumption is contamination of permeate by housing of membrane module or permeate pipes, which are made of plastics. But if you have any other ideas, don't hesitate to give them. And the membrane or pipe age could have an impact on the retention, as we saw in the last application, and this could also corroborate this assumption. So finally, if you want more information on this topic, please feel free to have a look at these 2 last papers we published. I wanted to thank all the students who worked on this project and our financial and technical support and partners, as you can see here. And of course, I thank you for your attention.